Okay, it's time for today's lecture. Thank you very much for attending this class. I really appreciate your participation. And again, thank you very much for showing up on time, okay? Attending classes on time is not an easy thing for college students, okay? But so that is why I want to thank you for showing up on time. I really appreciate it. Okay, now let's review what we discussed in the end of previous week's lectures. Right now we want to talk about, in the context of the first order systems, we want to talk about the relationship between pole, bandwidth, and speed of response of the system. Apparently, speed of response is a time domain characteristic, a time domain property. Bandwidth, however, is a frequency domain measure, okay? If you want to know what the bandwidth is for a first order system, we have to go to the frequency domain. Pole, however, represent one of the most important parameters of the transfer function, which is typically defined in the X domain. Now we want to connect the dots, connect these three important measures or properties together so we can view the function of the system in a more integrated framework. Now, I think we have seen these slides many times. Here, I just want to review the fact that we can represent the transfer function in the X frequency domains, okay, by dividing a transfer function into two parts. The first part, or the first portion, is, of course, the amplitude spectrum, and the second part is the phase spectrum. All the mathematical details you need to understand these concepts are given in this page, and we have gone through this page multiple times. So I don't want to repeat what I have already said many times. But let's just look at a simple example which we saw before, which is the first order system, okay? This is the representation of a first transfer function of a first order system given in the time domain. Apparently, the time constant now is tau, and the pole is located at 1/tau, okay? Now, if I want to know the amplitude spectrum, what I can do is I create magnitude plot of the body diagram, which means the first thing I do is I take the magnitude of the transfer function, which is this, and I take log, and I multiply it by 20, okay? And this is what I get. Based on this information, I can already be able to plot the magnitude plot of this first order system. But as I said before, we can also set up asymptotics for this function by assuming omega to be very small or omega to be very large. Very small or very large, respect to what? Respect to the location of the pole, okay? Respect to 1/tau. Remember, tau is the constant. So assuming this is the first order, so the transfer function of the first order system that is being considered, and this is, I'm sorry, this is its phase response, and this is amplitude response or magnitude plot of this transfer function, okay? So the break frequency or the corner frequency is actually located here. Remember, again, as I said many times, now tau is the time constant, all right? So when tau is smaller, then this part will extend it further to the right, which means I have larger bandwidth, all right? Now, assume here in this particular page, T is actually tau, which is the time constant. And this is the unit step responses of first order systems with different time constant. As you can see, the smaller the time constant, the fast the unit step response. What is the time constant? Okay, the time constant of first order system is a measure of how fast the system responds to a change in its input. Okay, now this statement, of course, referred to unit step response. Let's review its definition. It is defined as the time required for the system output to reach 93.2% of the final steady state value, okay, after each step response is applied. So the key number here is 93.2%, all right? Now, the concept, the utility of the definition of the time constant is that a smaller time constant indicates fast response, okay? By contrast, a larger constant indicates a slow response. So time constant is actually a measure for the speed of response of a first order system. Remember that here, it seems that time constant is defined for first order system. This statement is, of course, true, but the concept of time constant is also applicable to higher order systems. Okay, so in many cases, if you want to express or represent or characterize or quantify how fast a system is, you provide its constant. Okay, now time constant, okay, from this plot apparently quantify the speed of response of a first order system. Now, as you can see, for this first order magnitude plot, it had everything to do with the bandwidth of the system. This particular figure demonstrates that bandwidth of a first order system is controlled by the pole location. Now remember, for the first order system under consideration, the pole is located here, all right? So the distance between the pole and the imaginary axis is actually 1/tau, okay? That is the reason why bandwidth is controlled by the first order, by the pole location. At least this is true for first order system. Okay, the break frequency, which is here, is apparently omega equals to 1/tau. Okay, now after that, the magnitude begins to drop at 20 minus dB per decade. Okay, which means that whenever the frequency increase by a factor of 10, the decibel value drop 20 dB, all right? Okay, now what does it tell us? Remember, in the beginning, I told you that our goal here is to relate these three important parameters, okay? So, from this figure, it tells us a pole closer to the imaginary axis, which means it has smaller 1/tau, and hence larger time constant. produce narrow bandwidth, all right? Because in this case, when it is smaller, then, for example, its magnitude plot changes from this, for example, to this, okay? So the bandwidth apparently is smaller, okay? So smaller time constant correlate directly to larger bandwidth and vice versa, all right? Now let's look at an example. Here I have two first order systems, okay? The only difference is on their time constant. Here, for system 1, the time constant is apparently 1. For system 2, the time constant is 3. Now, from what we have just learned, we expect system 1 to have fast response, higher speed of response. And this is exactly what we see in figure B, right? Here, system 1 has faster response because it reached the target faster, okay, in less time. Now, this is for unit cell response, okay? Now, if my input, which is the target output, is this, okay, a linear function, and these two curves represents the responses of these two systems. Again, as expected, system 1 is faster than system 2, okay? And because of this, the difference, that is, the tracking arrow of system 1 is also smaller than the tracking arrow of system 2, all right? Because it is faster, so it is more capable in catching up with the moving target, all right? Remember, now the command is not a fixed constant. It is a function of time. And that function of time has only one trend. It increases linearly with time, all right? Now, these two figures are results presented in the time domain. In the frequency domain, based on this figure, we know that we expect this to have system 1 to have larger bandwidth, right? Because its port is located at x equal to -1. So its break frequency is here, system 1, all right? In comparison, system 2 has a time constant of 3, and its port is therefore located at 1/-3. So this is the corner frequency or the break frequency of system 2. So by comparing these two curves of magnitude plots, okay, it is easy to see that system 1 has larger bandwidth, okay? So a larger bandwidth from the above observations mean that the system can pass wide range of frequencies, okay, including high frequency components. That is exactly what we have in this figure, okay? Larger bandwidth means system can pass wider range of frequencies, okay? A fast state response, that is higher speed of response, requires system to process high frequency content of the unit input function very quickly, okay? Now, if you want to have a fast system, then the number one condition that this system need to satisfy that is it should be able to process high frequency components or high frequency contents of the input. Okay, all right. So large bandwidth means higher speed response. All right. Therefore, increasing bandwidth usually improve tracking ability, as demonstrated in this figure, because system 1 has larger bandwidth. Therefore, system 1 has smaller tracking error because it is faster. Therefore, it is more capable in catching up with this moving target. All right. Now, it can improve tracking error, but can reduce stability margins. Okay. This apparently is a side effect because stability margins such as phase margin and gain margin are important for the robustness of the system. Okay, so designer has to balance between balance between speed of response and the stability margins. We will talk about this consideration further in the later part of this lecture. Okay, now another example. Again, two first order system. Here, time constant is 1. Here, time constant is 5. So, two magnitude plots. Again, because it has smaller time constant, therefore, system 1 has larger bandwidth. As a result, system 1 has fast unit state response. Okay, so as the pole shifts further to the left, okay, that is further away from the imaginary axis, the time constant decreases and the system bandwidth increases. Okay, now bandwidth, there are some important key points that we need to be aware of. That is bandwidth, the connection between bandwidth and noise rejections. A higher bandwidth system will also pass more measurement noise, okay, which often resides at high frequencies, okay. So high bandwidth improves trackings, make the system more sensitive to noise. So that is another drawback of a system with large bandwidth. So you want a system to move fast, to have higher speed of response. Okay, it is difficult to do that, not just because you need, for example, more powerful actuator, smaller tungsten, but also you need to consider is the sensitivity of the system to noise and the reduction of stability measures such as phase margin and gain margin. Okay, now there is a practical rule of thumb for determining bandwidth. Bandwidth is often taken as an approximation upper bound on the frequency inputs in the system can track with small steady state error. So the first thing is that I need to know how fast my input is. Okay, now apparently one of the fundamental goals of my control system is I want my output to follow the command given by the input. That is the very fundamental goal of a control system. Follow the command. Okay. Now, apparently, steady state errors in most cases is inevitable. It's just a matter of how large it is, assuming that you have already set up a settable upper bound for the steady errors. Okay. Now, then you need to increase your bandwidth until this steady state error can be reduced to the specifications that you set up. Okay, now this is examples. Let's say this is the input, okay, and these are the responses for these two systems, okay. Is the time constant small enough? It depends on, is this steady state error small enough? If this steady state error is not small enough, then you need to decrease the time constant further, which means you need to increase or extend the bandwidth further. All right, that is the rule of thumb. Okay, but there, as I said before, okay, you also need to consider the factors of noise. Okay, you also need to consider stability measures such as phase margin and gain margin. Okay, now we want to talk about we want to talk about the same issue. That is the interconnections or the interactions between pole, bandwidth, and speed. But now our focus is now just on first order system. Here we want to focus on second order system, which is actually the most important systems and when it comes to control applications. Now, this is the transfer function of a standard for second order systems. Now, in order to determine its bandwidth, that is omega b, let's assume the bandwidth is omega b, and by definition, okay, the magnitude of the ratio of the output to the input should be 0.707 at the bandwidth frequency, all right? That is because 20 log 707 is equal to -3 dB, okay? Now, why 0.707? Because 0.707 is equal to 1 over square root of 2. Why 1 over square root of 2? Because if you take the square of this number, it gives you 1 over 2, okay? Why do I take the square? Because the definition is actually defined based on the consideration of power, okay? So this specification actually refers to the frequency that the output signal only reserve half of the power of the input signal, okay? So this frequency of bandwidth sometimes is also referred to as half power frequency. Okay, half power frequency. Okay, now this equality comes from the definition of bandwidth. All right. Now, what I do next is I just rewrite this value. Okay, and omega n squared remains to be omega n squared, and the magnitude of this complex number is this, okay? Then when I multiply this, then the next thing I do is I square both sides of these equalities. So this term become omega n to 4. And this, of course, become 0.5. And this is this after taking square, all right? And then remember, what I want to do is to determine the unknown omega b, okay? Instead of solving omega b directly, I reformulate this equality by dividing everything by omega n to 4. And this is what I will get. Now, think of this as x. All right? Think of it as x. What I will get is a second order polynomial in terms of x. Then I can solve x from this polynomial. And this is exactly what I get. Okay? This is what I get by solving such a polynomial. And from here, we can set up this final result. Okay, what do we know, or what do we learn from this final result? The number one thing that we learn from this equality is that bandwidth is actually proportional to natural frequency of the second order system. Let me put it in another way. For a standard second order system, its bandwidth is actually proportional to the natural frequency of this standard second order system. This is one of the reasons why we have said it again, and again. The most important two parameters of the second order system are natural frequency and damping ratio. Okay, why do we choose this as these two parameters as two of the most important parameters of the second order system? Because it relates to many important characteristics of the second order systems. For example, here, you know that the larger natural frequency, the larger the bandwidth. That's number one. Number two, damping ratio is also has something to do with damping, but bandwidth has also something to do with damping ratio. But this equality is too complex to visualize such a connection. So we just plop them out, okay? Now, here, the horizontal axis is damping ratio. The vertical axis is actually the ratio between bandwidth and natural frequency. As you can see, for a system with given natural frequency, when eta increases, that is, when I have larger damping ratio, actually has smaller bandwidth. That means bandwidth decreases with the damping ratio, okay? Now, since this representation is mathematically too complex for us to visualize, then we can, to simplify this problem, someone has come up with this linear approximation, which is this blue curve. As you can see, the discrepancy, that is the difference between the real curve and this approximation curve is actually very small when damping ratio is in the interval from 0.3 to 0.8, all right? Now, this blue curve is actually comes actually from this straight line, okay? All right? From here, again, you can see that bandwidth decreases with damping ratio because as eta increases due to these negative signs, the value of omega b goes down, all right? So now, is this result unexpected? Of course not, all right? Because we all know that bandwidth is a measure of the speed of response of the system. So we expect if a system has larger bandwidth, we expect this system has higher speed of response. And damping ratio, when you increase damping ratio, you increase relative stability at the expense of speed. So typically, higher damping ratio means slower response. Therefore, higher damping ratio now leads to smaller bandwidth. So it makes sense that we have such a result. Now, this is what we have. This is just, if another way to represent this equality, all right? The only difference is that this omega b here is written as omega BW. BW, of course, denote bandwidth, all right? Now, here, this equality can also be written as this or this. Now, here, it tells us that bandwidth in settling time is actually inversely correlated. That is, the larger the bandwidth, the smaller the settling time. Similarly, in this equality, it is also very easy to see that the larger the bandwidth, the smaller the peak time, all right? So again, these two results confirm the conclusion that higher bandwidth means fast speed of response, okay? So when natural frequency goes up, bandwidth goes up, speed of response goes up, all right? Let's look at another example. Here, we are comparing two second-order systems with the same damping ratio. Both of these systems have a damping ratio of 0.5, but different natural frequency, since this term is actually omega n squared. So this says the natural frequency of this system is omega 10. Similarly, the natural frequency of this system is omega 30, okay? So we expect the bandwidth of this system to be 3 times larger than the bandwidth of the first order of the first system. Okay, so this is what we have for their magnitude plot. Okay, as expected, the second system has larger bandwidth compared to the bandwidth of the first system, right? Okay, so these are the results in the frequency domains, but we always have to come back to the time domain, because in the time domain, that is where things are really happening, all right? Because a system change with time, all right? Okay. Now, if I compare the unit step response, okay, this blue curve represents the unit step response of the first system, and this black curve, of course, represents the unit step response of the second system. Again, as expected, the second system is faster because it has larger bandwidth. Oh, now here another thing that you should know is that the overshoot of these two systems are the same. Okay, why is that the case? Because they have the same damping ratio. Okay, and for a second order system, okay, without any zero, okay, overshoot depends only on damping ratio. Okay, we saw that before. We talked about that before. All right. Now, let's introduce another concept related to bandwidth. That is working frequency bands. What do we want to talk about working frequency band after knowing that bandwidth is already a very bandwidth has already been defined, and we already know the impacts of bandwidth on the speed of response of the system. Because when we talk about bandwidth, the typical definition of bandwidth is this so-called -3 dB definition. That is, let's assume at a low frequency, the output of the system is 0 dB. And then when we in defining the bandwidth, we need to locate the frequency where this curve, that is, this magnetic plot, drops from 0 dB to -3 dB. All right. So this is the definition of bandwidth. All right. Now, this definition is not universally true because, I'm sorry, we saw the frequency response of a loudspeaker before. All right. Now, from the beginning, this speaker is a physical system, but in the low frequency range, its output is actually very, very small. It's not 0 dB, right? Therefore, you cannot expect it produce strong bass from such a small bookshelf loudspeaker. Is just physically impossible. All right. So in this case, the bandwidth, in this case, the -3 dB bandwidth definition, okay, it doesn't seem appropriate, okay, because the effective frequency range this loudspeaker can operate, can function normally, actually is in this range. Okay, so based on such of observation, here we want to introduce you a concept, what we call working frequency band. All right. Now, this is the magnitude plots of many second order systems. Okay. The reason why we have a family of curves is that we have systems with different damping ratio. Remember that the resonant peak of such a second order system depends only on eta, only on damping ratio. Okay. Now, what is the working frequency band all about? The working frequency band is the practical range of useful operation. All right. The working frequency band includes all frequencies for which the closed loop system meet the relevant performance specification. All right, such as the bookshelf loudspeaker we just saw. Okay, what is relevant performance specifications? It depends on your requirement. But for the loudspeaker we just saw, it means the speaker should be able to produce sufficient amount of sound pressures or sufficient amount of volumes in that frequency. All right. Now, in simple terms, the bandwidth is a mathematical cutoff. That is, you need to specify cutoff in the frequency domain to define the working frequency band. And let me say this statement again. In simple terms, the working frequency band is the practical range of useful operations. For example, for this first order system, this is the asymptotics of the magnitude plot of a first order system. We can think of this part as the bandwidth because input signals, whatever its frequency is, as long as its frequency is within this frequency band, it can be reproduced without any reduction in terms of magnitude at the output end of the system. Okay, I'm sorry about the Mandarin. Okay. This four character actually means working frequency bands, and this means noise frequency bands. That is the reason why we want to decrease the magnitude of this system in this frequency band is that we expect the frequency contents of noises will appear in this frequency band. Since we want to minimize the influences of the noises on the system, so we don't want the system to magnify or to amplify the noise. On the contrary, we want to reduce the impact of these noises, all right? So in this case, we can think of bandwidth, this portion of the interval frequency band as pass band, okay? And for this part, this frequency band is for noise attenuation. Now, the above-body magnitude plot shows that frequency response of a first-order low-pass system, all right? Now, at the low frequencies, the gain is approximately 0 dB, right? This region is called the pass band or working frequency range because here, everything is 0 dB. Every frequency component in this so-called working frequency bands can be faithfully reproduced at the output end of the system. Now, where the system accurately passes the desired signal at the frequency omega equals 1/2, this is the corner frequency of the first order system. The gain has decreased by about 3 dB. This point defines the bandwidth of the system. Now, remember, this is the asymptotics of the magnitude plot, all right? It's not the real magnitude plot. The real magnitude plot actually looks something like this, okay? And here is actually about 3 dB at the corner frequency, okay? At the corner frequency, the dB value of a first order system is approximately -3 dB, all right? This point defines the bandwidth of the system. So for the first order system, the bandwidth is actually 1/tau, where tau, as I said it many times, is the time constant of the first order system. At high frequencies, the gain decreases as -20 dB per decade, which means whenever you increase the frequency by a factor of 10, the dB value drops 20. This region is where high frequency components of the input signal is strongly attenuated, okay? So we cannot expect the high frequency components of our input to be faithfully reproduced at the output end of the system, all right? Most real control systems exhibit a low pass response, okay? When it comes to real engineering systems, such as mechanical systems, electrical systems, and things like that, these real physical systems, when it comes to the frequency domain, they actually exhibit a low pass response. Most of them are what we say low pass filters, which means it cannot respond effectively to high frequency inputs, all right? Now for the second order system, this is a working frequency band. for the first order system. All right. Now, for the second order system, the minus 3D definition is again not appropriate. Why is that the case? All right. The bandwidth calculation derived from the minus 3D definition is still mathematically correct. Mathematically, this definition is okay, but its interpretation as meaningful performance matrix for very lightly damped system become questionable because the response is dominated by the resonant peak. All right? If I use the minus 3D definition to determine the bandwidth of this or such for a second order system, then the bandwidth based on such a definition will look something like this. This will be the frequency of bandwidth, okay? And this is actually the bandwidth of this system. And unfortunately, with such a definition, this frequency C-band actually include this resonant region. And we don't want that, okay? We don't want system to respond like this because remember, this represents the ratio between the input and output. Ideally, we want the ratio between the input and output to be 0 dB because we want that number to be 1 because the goal of our control system is to make the output of the system follow the input command, reproduce the command provided by the input, all right? So this, of course, destroys that property. So this is typically a region we don't want to get involved. It will involve very strong response, okay? 20 dB higher than desired, right? It can even destroy the machines that we use due to this overly strong response, okay? So the reasonable working frequency band is actually in this portion of the frequency domain, okay? Not here, okay? Not this, okay? All right. So this is the reason why that this minus 3 dB definition become questionable. Its interpretation become questionable, okay? Now, for lightly damped systems, based on this concept, it can be mathematically proven that the bandwidth is approximately 2 eta omega n, all right? Know that the pole of a second order system is located at this, all right? So eta omega n is actually the distance between this pair of complex conjugate poles to the imaginary axis, all right? So when this pair of poles is further away from the imaginary axis, this number becomes larger and bandwidth become larger, and then the speed of response of the system becomes faster, all right? So a formal definition, a more appropriate definition for the bandwidth for so-called lightly damped system, such as system with a damping ratio of 0.05 or 0.01 or 0.15. These are all lightly damped system because when we say lightly damped, we mean its damping ratio is very, very small, at least relatively small, okay? All right, so therefore, keep this in mind. because in practice, identify working frequency band is very important in designing a control system. All right, let's take a 10-minute break because it's already 10 o'clock.